Hello everyone. Today we will continue the introduction about the route ring. In this lecture, we will focus on the intersection between a line and a curve, the super elevation, and the vertical curves. In transport system, it's very common that a straight segment is intersected with a curved segment. So it's very important for us to identify the intersection between the straight segment and the curve. The figure here shows one example about the intersection between the straight segment and the curve. We want to find out the location of the intersection and the relative angles of the straight segment with respect to that curve. So in this case, we are given the information about the curve and the straight segment. That is, we are given the whole curve AOB, so we know the radius of the curve and the intersection angle. Also, we are provided with the information about the straight segment XP prime. And we are provided with the information of the intersection between the straight segment and the vertex segment A to V, and the intersection is P prime, so we measure the distance from A to P prime. And we want to find out the information of the segment from P prime to P and the angle of theta, which is the angle between the straight segment and the radius from O to A. To solve this information, we first need to consider the right triangle A, P prime, and N. The angle of A and P prime is set as beta. For this right triangle, we can find out the length of NA and NP prime. So NA equal to AP prime, which is measured in the experiment, times tangent alpha, which is the angle between the straight segment and the vertex segment. It's also the value of the angle here, AP prime N. We can find out the length of NP prime as AP prime divided by cosine alpha. Also, for this triangle, we know that alpha plus beta equal to 90 degrees. Now, in the next step, we want to find out the length of ON, which is pretty simple. ON equal to R minus NA, that is R minus AP prime times tangent alpha. And in the next step, we want to consider the triangle OP and N, assuming that the angle of MPO is 5 and the angle of NOP is theta. The rest angle here will be 180 degrees minus beta. We also have beta equal to 5 plus theta. So with this information, we can use the triangle NOP to list the set of our equation. That is ON divided by sine phi equal to MP divided by sine theta equal to OP divided by sine 180 minus beta. We know that OP is R, and sine 180 degree minus beta is just sine beta, so that is r divided by sine beta. So we can further derive the information of sine phi as on divided by r times sine beta. And with this information, we can find out the value of phi. Here, beta equals 90 degree minus alpha, which is the equation we showed in the previous one. And with the value of phi, we can find out the value of theta as beta minus phi. And that one equals to 90 degree minus alpha minus phi. So that's the way for us to find out the value of theta. And then we want to find out the length of P to P prime. With that, we want to know the length of N to P, as we already calculated the distance of NP prime. So we have NP equal to R times sine theta divided by sine beta. This one comes from the equation that we showed here. And we can find out the value of NP and then derive the length of P to P prime as NP prime minus NP. So that's the way for us to get P to P prime and theta for the intersection. We can also apply the coordination to estimate the value of theta and P to P prime. With that, we have to consider the polygon P prime, A, O, and P. The table below shows the distance of each segment and the direction. Also, we can estimate the departure and latitude. All the informations are given except the value of theta and P to P prime. So for the polygon P prime OA, if we consider the summation of the latitude, we will have P prime plus R times cosine times sine alpha plus theta minus P prime A times cosine alpha minus R times sine alpha equal to 0. And we also have the equation for the departure. That is P prime A times sine alpha plus R times cosine alpha plus theta minus R times cosine alpha equal to 0. So we can solve these two equations and find that cosine alpha plus theta equal to R times cosine alpha minus P prime A times sine alpha divided by R. We know the value of R alpha and AP prime. Then we can find out the value of theta. In addition, we can get the value of P to P prime as PA times cosine alpha plus R times sine alpha minus R times sine alpha plus theta. Similarly, all the variables on the right side are given or calculated. With that, we can find out the value of P to P prime. So that's the way for us to find out the intersection between the straight segment and the curve. In transport system, when the vehicle or the train is moving along the curved segment, a horizontal centrifugal force will be generated, and this will generate some risk issues for the movement of those vehicles or the trains. In that sense, when we design the track or the road pavement, we have to make sure that the outer edge is super elevated, which will be demonstrated as the line here. This is the inner and this is the outer. We will have a certain slope applied to the pavement. The design of the super elevation is applied to prevent the centrifugal force. So in the construction of the pavement, we have to keep the slope for the pavement surface. And the super elevation E is applied to identify the slope. The vertical distance will be E over 100 with respect to the unit horizontal distance. The design for the railway and freeway are different. For railway, we have E equal to 0.00067 times V square times D. Here, V is the speed of the train, and D is the degree of curvature. For the freeway, we have two different definitions. If we are using the international system of unit, there would be E plus F equal to V squared divided by 127 R squared. And here, F is the lateral friction factor. And we can also find out the degree of the curvature with the arc definition as 730,000 E plus F divided by V squared. If we are using the imperial system, then we have E plus F equal to V squared divided by 12 times R squared, and dA equal to 85,660 times E plus F divided by V squared. So that's the way for us to define the super elevation for the railway and the freeways. The design of the vertical curve is another important component of the road surveying. We know that in reality, the elevations at different locations of the road will be different. So the segments on the road will have different slopes. In order to prevent the abrupt changes from one segment to another segment with a different slope, we need to introduce the vertical curve to build the connection smoothly. And the figure here shows one example about the design of the vertical curve to connect the segment from A to V to V to B, where the slope of AV and VB will be different. The design of the vertical curve can be conducted based on the equation of the parabola, assuming that we have two straight segments with different slope. And we say that the vertical curve should start from the point 0 and end it at the point L. And here y is the elevation. And we want to have the curve to connect these two segments smoothly. Now with the equation of the parabola, we can define the curve as the function y equal to fx. We can find out the second order derivative of y to x to be on a constant value, say it's r. With that, we can derive dy over dx as rx plus another constant variable h. Also, we have to apply the initial condition. At x equal to 0, we have the slope of the curve as dy over dx equal to the first segment. Say the slope is g1. For the second one, it's g2. So we have dy over dx at x equal to 0 equal to g1. So that is r times 0 plus h, which is h. So we have h equal to g1. And at x equal to L, we have dy over dx equal to g2. That is r times L plus h. With that, we can derive h equal to g1 and r equal to g2 minus g1 divided by L. So with these two information, we can find out the function to describe fx. So we have y equal to g2 minus g1 divided by L times 2 times x squared plus g1 x plus capital C. And here capital C will be the elevation at the initial point. So this is a capital C. And we can also find out the location where we have the highest slope for that curve, which would be dy over dx equal to 0. With that, we can find out the location x prime equal to minus g1 over r. Now let's check one example to see how we can use the equation of the parabola for the design of the vertical curve. Assuming that we have two straight segments with different slopes. G1 is 1.25%, G2 is minus 2.75%. And we know the distance from the start to the end point of the vertical curve as 200 meters. Also, we know the elevation at the vertex as 270.119 meters, and the horizontal distance from the start point to the vertex is 100 meters. With that, we want to find out the equation to describe the vertical curves. So first of all, we need to identify the elevation at the initial point, which is a capital C in that equation. So that is the elevation of the vertex minus the slope of the segment times the distance from A to, actually horizontal distance from A to V. So that is 270.19 minus 0.0125 times 100, which will give us the elevation as 268.940 meters. And then we can find out the value of R for the equation of the parabola. We have R equal to G2 minus G1 divided by L. So that is minus 0.0275 minus 0.0125 divided by 200. So we have the value as minus 2 times 10 to the power of -4. Then we can call the equation y equal to r over 2 x squared plus g1x plus c. In this case, we have minus 0.0001 x squared plus 0.0125 x plus 268.940. So this would be the equation to describe the designed vertical curve. The vertical curves can also be designed based on the vertical offset from tangent line, which is shown as y prime in this figure. Y prime represents the difference between the tangent line A to V and the curve AMB. We need to identify the value of y prime as a function of x for the design of the vertical curve. Basically, in this figure, we set that y prime as negative. And then we can find out the distance from the tangent line to the elevation of the starting point BVC as y minus y prime. And now we just assume that the horizontal line at the level of BVC is the one we're going to use. In that sense, the elevation at BVC can be assumed as 0 to simplify analysis. So based on the distance from the tangent line to the x-axis, which is y minus y prime, and if we are given the distance from the starting point to the point we measured, that will be x, then it will be the same to the slope of the tangent line, which is the g1. So we can derive the function for y as x times g1 plus y prime. Here you should know that y prime is negative. It represents the elevation difference from the tangent line to the vertical curve. We also know that y is the function of the x from the previous pages. So that is g2 minus g1 divided by 2l times x squared plus g1x plus capital C, as we assume that BVC is located at the x-axis, so the elevation is 0. We remove capital C from this equation. With this equation, we can then find out the formula for the vertical offset y prime. So we have y prime equal to g2 minus g1 divided by 2l times x squared. It also equals to half r times x squared. And then with this formula, we can find the value of y prime at the vertex, which is a point V. So at V, we have y prime equal to Vm. And also we know that at Vx will be half of the capital L, which is the horizontal distance from the initial point to the end point, that is AB. So we can derive the length of Vm based on the equation for y prime, that is g2 minus g1 divided by 2l times half L squared, which will give you the expression as g2 minus g1 divided by 8 times L. So that's the maximum offset for the vertical curve. In addition, if you try to consider the equation here and the formula here, by dividing formula 1 to 2, we can then find out the expression of y prime as 4x squared divided by L squared times Vm. So that's another expression for you to find out the value of y prime at all the locations along the vertical curve. Now let's see how we can use the vertical offset method to solve the problem in the first example, which is shown in the figure on the right. In order to apply the vertical offset method, we first need to identify the elevation along the extended line of the two straight segments. So we have to identify the elevations of these stations. And then we need to find out the offset for each station between the tangent line and the vertical curve. For the calculation of the elevation along the tangent line, we can actually use the linear property of those straight segments. Based on the grade of the straight segment, we can identify the elevation at those stations with the information of the elevation at the initial or the end point. And the elevations will be listed in the second column in this table. And then we have to specify the distance from the station to the initial or the end point. And this is actually the horizontal distance. And that is the value of x we need to use for the calculation of the vertical offset. For the first 5 stations, we will consider the initial point BVC as the reference point, while for the rest 5 stations, we will consider EVC as the reference point. And then we can call the equation y prime equal to 4x squared divided by L squared times Vm, which is the fourth column here, little l, equal to half capital L. In this equation, we need to know the information of Vm. Actually, if you go to check the figure, you can find that Vm equal to half of Vc. And Vc is also half of the segment from B prime to EVC, say it's a V prime. So it's a half V prime. By considering the tangent line start from the point BVC, we can find out the value of VC. In this case, it's 4.0. So we can find out the value of Vm as 1.0. With that, we can then calculate the value of the vertical offsets, and then the elevation is estimated directly by summarizing the elevation along the tangent lines and the offset. So for example, for the station 17 plus 20, the elevation is 269.19 minus 0.04, that is 269.15. So that's the way for us to use the vertical offset for the vertical curve design. So that's all about the lecture today. Thank you very much for your attention. With that, we finished all the contents about the design for the horizontal and vertical curves. In the next lecture, we will focus on the estimation about the volume for the earthworks.